Welcome back, scholars. To be successful in Chapter 4, we're going to need to be able to solve inequalities, and inequalities that are a little more complicated than something like x plus 2 is less than 5. So those we can solve, those inequalities we can solve by isolating the x. But to solve an inequality that is quadratic in x, or has a higher degree of x, of the variable, than 1, we're going to have to use a special technique. Requires factoring, especially if you took trigonometry over the summer and never took a pre-calculus class. There's a chance you missed this critical topic, so you're going to need to watch as much of this video as you need to, or find other videos that work for you, so that you can answer the practice problems I post at the end of this video, and that I'll bring for you Monday when we come back to class. So if you feel like you already remember this, just stop after a couple of examples. If you can do a couple of problems, you're going to be fine. But you have to know how to solve an inequality that has degree 2 or higher. So I'm going to give you some key points for solving an inequality of degree 2 or higher. So number 1, I want you to So you're going to have an easier time if you can think about what the graph of this inequality would look like. It's going to help us understand how to find a faster method, a number, an algebra method to get the answer, but it won't really help us unless we really understand what's going on in the graph. So imagine this. I'm going to try to solve this inequality. X squared minus x minus 6 is less than 0. If I can think about what the graph of x squared minus x minus 6 looks like, I'm going to have an easier time. So I'm going to think of x squared minus x minus 6 as, looks like I can factor, that's x minus 3 times x plus 2. So that's the exact same function. I've just factored the left-hand side. That tells me if I want to think about the function y equals x squared minus x minus 6, it's going to have roots, it's going to have x-intercepts at x equals 3 and x equals negative 2. And I remember enough about parabolas from Algebra 1 that I know that since the leading coefficient is positive, this parabola is going to open up like a smile. And I know that the vertex has to happen exactly halfway between those two x-intercepts. So my vertex is going to be at x equals 1/2. I'm draw a vertical line. I could figure out exactly what the coordinates of the vertex are, but here's what I need to know. I have a, if you want to call it, an open up parabola that has x-intercepts at positive 3 and negative 2. So most of the time when we have to solve an inequality like this, it's going to be of degree 2, and we know that degree 2 functions, when they're graphed, create a parabola. So this brings us to the second thing I'm going to need you to think about. If you can bring these two things together, you're going to be in good shape. My original inequality that I wanted to solve was x squared minus x minus 6 is less than 0. So my second piece of advice here is to interpret that less than 0 to mean is negative. So what I'm really looking for, I'm looking for any x that makes this original inequality true. That's going to be any x which makes this parabola, x squared minus x minus 6, negative. So I could, now that I have a sketch, and again this is just a sketch, but it can help me a lot. Where is this parabola less than 0? So where is this parabola negative? Well, this is the part of the graph where the parabola hangs below the x-axis, and that happens between negative 2 and positive 3. So you can write negative 2 is less than x, which is less than 3, or you can, if you want to use parenthesis bracket notation, that's negative 2 with a parenthesis there, 3. If you're going to use parenthesis bracket notation, I need you to be really careful to remember that this is an interval that describes all the possible x's that are solutions to this inequality. It is not an ordered pair. I am not saying that negative 2 comma 3 is a point on any function. Negative 2 and positive 3 are x values, and this means that all the x values in between negative 2 and 3 are also solutions. Okay, so these are two things I want you to think about when you solve an inequality like this. But, to be fair, when we have to solve lots and lots of inequalities like this, we want an algebraic method to help us do this that's going to be faster than stopping to make a picture. Although if you get really good at making the graph, feel free to just use a sketch to help you answer questions like this. But we want to understand what the algebra that's happening here too, because we'll find that sometimes we have to apply it to a degree 3 or 4, or even some non-polynomial inequalities that we're going to want to solve, especially in chapter 4. So here's the algebra I do to solve this inequality. If we're going to think about that less than 0 to mean is negative, the only time a function can change from positive to negative, or from negative to positive, is by changing through 0. So, I'm sorry, I should correct that. The only way a continuous function can change from positive to negative, or vice versa, is to change through 0. So remember on the little sketch that I made, the interesting points on that parabola were the x-intercepts, because of the places where the y value is 0, where the output of the function was 0, and our function can only change from having positive inputs to negative inputs, or vice versa, if it changes through 0. So your very first step, we're going to need to use the zero product property. In order to use the zero product property, step number 1, you're going to have to make 100% certain that you have a 0 on one side of your inequality. None of what I'm about to show you will work if you don't have everything moved to one side with a 0 on the other. Your next step is going to be to factor. So remember that I already factored that other guy. This was x minus 3, x minus 2, oops, x plus 2 is less than 0. So what I want to do, I want to think about where I know this function equals 0. So probably in your head, if this were an equal sign, you would say, oh, I'm going to write two little mini equations, x minus 3 equals 0, x plus 2 equals 0. You're going to get two solutions. These are the two zeros. They're two very important numbers. But I don't want to write them down there because that would imply that I had an equal sign there, but I really don't. So I'm going to write them to the side. This is my recommendation, is that you make a number line for every problem like this. So I'm going to make a number line. The numbers I'm going to mark on this number line are the roots of this function. So the x values that make the output 0. Those are positive 3 and negative 2. And now if you think back to the sketch I made on the last screen, this is sort of a two-dimensional, well no, sorry, it's a one-dimensional projection of that two-dimensional picture I had. And it turns out that's exactly what we're going to do. We're projecting that parabola down into one dimension. So the question here is, if I have two things multiplied together, and I want the answer to be is negative, right? Less than 0 means is negative. Under what circumstance is that going to be true? Well, it's only going to be true if the two factors, the two things that we're getting multiplied together, have opposite signs. So there's a couple different ways that people think about this. I guess I use them interchangeably. So I'll tell you what I do. I start by looking at this number line I've drawn, and I notice that those two x-intercepts have broken my number line into 3 parts. So 1, 2, 3 sections. I'm going to choose an x value from each section, because the only way that my parabola could change from positive to negative is to change through 0. If there's only 2 zeros, and there's only 2 possible changes. And if I figure out if the parabola, the outputs of the function are positive or negative somewhere on that same section, it's got to hold true for the same the whole section. So I might do something like this. I might like x equal, let's see, I'll start with some positive numbers. What if I said x equals 5? That's a number that's in this section over here. I'm going to wish later that I hadn't circled that, so I'm going to undo that. Okay, if x were to equal 5, I'm going to have 5 minus 3 times 5 plus 2. Notice that I've replaced the x's with 5s. So 5 minus 3 is 2. 5 plus 2 is 7. And the only thing that's really interesting to me, it's not the value I get, but it's whether this result is positive or negative. So if I multiply 2 times 7, that's a positive times a positive, the result is going to be positive. And I mark this whole number line section with a plus sign for positive. Now I'm going to choose another x value, one from the next interval down. Oh, it'd be nice and easy if I use 0. That's between negative 2 and 3. So I'm going to have 0 minus 3 times 0 plus 2. You don't even have to use this much detail if you get to the point where you can do this substituting in your head. So that's a negative times a positive. 0 minus 3 is negative 3, which is negative. 0 plus 2 is positive, positive 2, which is positive. A negative times a positive is going to make a negative result. So any number I pick on that middle section from negative 2 to 3 is going to give me a negative result. I could try that last interval. If I pick a number less than negative 2, so like negative 3, that's going to be negative 3 minus 3 times negative 3 plus 2. That's going to be a negative number times another negative number. A negative number times a negative number is a positive number. So here we have. So once I've drawn this chart, and we call this a sign chart, S-I-G-N chart, I can go back to my original problem and say, well, I was looking for any place where x squared minus x minus 6 is less than 0, is negative. Where is it negative? On this section of the number line that I gave a big negative sign to, and that's everywhere between negative 2 and 3. So I'm going to write negative 2 is less than x, which is less than 3. Which is the same answer we got when we were looking at the picture before. But now we're going to take this technique and apply it to a new problem.